8, 7, 6, 5, 4, 3.
Suppose you had an integral like this to evaluate. F is a complex function, and C, let's say, is the unit circle. That's the circle whose center is at the origin and whose radius is 1. Well, I'm sure that you could think of at least one way of doing this integral. You could parameterize the circle by taking zeta equals e to the I theta, and you could substitute into the expression, and then you would have two real integrals to evaluate. But I'm sure that if I gave you f for f, the exponential function, so it's the integral of e to the zeta d zeta over c, then you wouldn't tackle it in that way, because I hope you would remember Cauchy's theorem, which tells you that the integral of an analytic function around a closed contour is 0. You see, we've already begun to develop some indirect methods for evaluating contour integrals in the course, and the purpose of this program is to introduce some more indirect methods, and in fact to introduce a line of argument that's going to occupy us for the next 3 units in the course, units 8, 9, and 10, all to do with evaluating integrals around closed contours. Cauchy's theorem is one example. Cauchy's formulas give us some more methods for evaluating integrals. You remember Cauchy's formulas? They relate the value of a derivative of a function with an integral. If f is analytic on a region R, C is a circle in R, Z is inside C, and the value of the nth derivative of f at Z is n factorial over 2 pi I, the integral around C, f of zeta over zeta minus z to the n plus 1 d zeta. You see, we can read that, as it were, from right to left and use it as a method of evaluating a certain kind of integral. Let's have an example of that. Let's take the integral around the unit circle again of cos zeta over zeta d zeta. Now then, in this case, we've taken z to be 0, n is 0, and the function f is the cosine function. So to evaluate this, I take 2 pi I over 0 factorial times the value of the cosine function at 0, cos of 0, and of course that gives me 2 pi I. 0 factorial is 1. Another example, integral over c cos zeta over zeta squared this time. Z is 0 again, same function, but this time n is 1, so we'll want 2 pi I over 1 factorial times the value of the derivative of the cosine function at 0, that's minus sine 0, and so this time we have 0. So there we are. Now, a couple of points about that process. The first is this. Up to now in the course, we have emphasized very much the importance of analyticity in complex functions. But of course, Cauchy's theorem tells us that integrating analytic functions is a waste of time, because you always get 0. So when we talk about integrating functions, complex functions around closed contours, we're interested in functions only if they fail to be analytic. Let's look back at my first example again. Cos zeta over zeta. You see, this function, well, it fails even to be defined at 0. And of course, that's a point inside the unit circle. Now, we say that a function which sort of misbehaves in this particular way, we say that a function like this has a singularity. And here's the definition of singularity. If the function f is analytic on the punctured disk, naught less than mod z minus alpha less than r, but fails to be analytic on the whole disk, mod z minus alpha less than r, then we say that f has a singularity at alpha. Let's just look back at this function cos zeta over zeta. See, it's analytic everywhere except at the origin, where it fails to be defined. So it's certainly analytic on, for example, this punctured disk. That's this disk with the origin removed. But of course, it fails to be analytic on the whole disk. So that function certainly has a singularity at 0. So when it comes to evaluating complex integrals of complex functions around closed contours, we're only interested in functions which have singularities. My second point is this, that almost never in complex analysis do you evaluate integrals by doing any integration. So we've already had two examples of this. The use of Cauchy's formula enabled us to turn the evaluation of an integral into something much easier, namely evaluating a function or a derivative of a function at a point. Now the methods that we're just about to begin to develop in the course use the same sort of idea, but they use it in the context of series rather than just working with the derivatives themselves. Let's just see how that works. Up here I've got Cauchy's formula written down again. Z is 0 this time. And the thing that you must recognize is that this term on the right-hand side is, of course, the coefficient of z to the n and the Taylor expansion of the function f about the origin. So one thing we could do, instead of calculating derivatives, if we knew the Taylor expansion of the function f, then we could just scan along until we came to the coefficient of z to the n, and 2 pi I times that would give us the value of the integral. So if you're better at evaluating Taylor series than you are doing differentiation, that gives you another way of evaluating integrals. Here's another example. Integral over unit circle again, e to the zeta sine zeta over zeta cubed d zeta. Now if I'm going to evaluate that integral by using Taylor series, I must find the Taylor series of this function. I must look at the coefficient of z squared, because n is 2, multiply that by 2 pi I, and that will give me the value of the integral. Well, how do I calculate the Taylor series? E to the z, 1 plus z plus z squared over 2 factorial, and so on. Sine z, z minus z cubed over 3 factorial. Sorry, rather a rough 3 there. To find the Taylor expansion for e to the z sine z, multiply the 2 power series together. Well, I only need to multiply out a few terms. First term, there's no constant. The first term I get by multiplying those two together. That gives me a z. The next term, there's a z squared coming from there, and those are the only z squared terms, because this one is going to give me a z cubed. And then the next term is something times z cubed, something times z to the 4th. The coefficient of z squared is 1. 2 pi I times 1 is just 2 pi I. The value of that integral is 2 pi I. So there we are. That's a method, another method for evaluating integrals. There's just one slight possibility of confusion in that particular process, and that's this. The thing that we calculated the Taylor series for was the thing on the top. The thing that we're trying to integrate is this whole thing. And really, in a way, it'd be much better if we could deal with the whole function, the whole integrand, rather than just with the thing on the top. How can we do that? Well, let's try and find some sort of series for e to the z sine z over z cubed. What can I do? Well, I could just take a factor 1 over z cubed times that series, and that will give me 1 over z squared plus 1 over z plus a constant term plus something times z plus something times z squared. and so on. Okay, I think we just better pause for a moment and think about that a little. I've got some sort of a series expansion for the function e to the z sine z over z cubed. And it's a series expansion in that this series must converge to e to the z sine z over z cubed, provided z is not equal to 0. That's the first thing. The second thing is, it's a little bit unusual. It's not the sort of thing you're used to seeing. And that's because we got terms in 1 over z present. And of course, this reflects the fact that this function has a singularity at 0. Now, this sort of series, this series which involves terms in 1 over z, is called a Laurent series. And it's a sort of a generalization of the Taylor series for a function which has a singularity. So here we have the Laurent series for the function. Now, when I calculated the integral before using the Taylor series, it was the coefficient of z squared that mattered. Now, in the Laurent series, that term has turned into the 1 over z term. It's 1 over z cubed times z squared. So in the Laurent series, what I have to do is pick out the coefficient of 1 over z. So here's the program. If we have a function which has a singularity at the origin, and we want to integrate it around the unit circle, we expand that function as a Laurent series and pick out the coefficient of 1 over z, and it always turns out to be 1 over z, in the Laurent series, multiply by 2 pi I, and that's the value of the function. So there, I've outlined a method for evaluating integrals to you, and of course, the next thing that we have to do is prove a little theorem which actually shows that the method is valid. And the theorem that we want to prove is this. If f is a function which is analytic on the punctured disk, 0 less than mod z less than r, and has a singularity at the origin, then it has a Laurent series, and that looks like a sub minus 2 over z squared plus a sub minus 1 over z plus a0 plus a1 and so on, and those are a's then are constants. And in particular, the coefficient of z is given by the formula integral over c f of zeta d zeta is 2 pi I a sub minus 1. In a moment, I'm going to come back and talk about the proof of that theorem. But before I do so, I'd like to consider just one more example. You see, the examples that I've given you so far are all ones which I could, in fact, have done by using Cauchy's formulas. But let's have a look at another example. I take the integral over c, 1 over e to the zeta minus 1 d zeta, and the integrand this time is a function which is not in the right form for you to be able to use Cauchy's formula directly. Nevertheless, it's a function which has a singularity at 0. E to the 0 is equal to 1, so this function is not defined at 0, but it's analytic everywhere else. And in fact, the method of using Laurent series applies to this sort of integral, as well as to the other kinds that we've been talking about, and so we really have a useful generalization then at our disposal. So then, the thing is to prove this, in fact, fairly complicated theorem about the existence of Laurent series. And what I want to do in the next few minutes is to just give you a sort of an outline of the proof of Laurent's theorem, sufficient so that you can read the proof in Unit 8 without being thrown by when it comes to reading the calculations, by what's actually going on. So the proof of Laurent's theorem is in fact rather similar in lots of ways to the proof of Taylor's theorem. And the first thing that I'd like to do is to remind you about the proof of Taylor's theorem. On the left-hand column here, we've got the sort of steps in the argument for the proof of Taylor's theorem. And on the right-hand side, we've got the calculations, if you like. We start off with a function which is analytic, this time on a disk, an open disk. And the first thing we do in proving Taylor's theorem is to use Cauchy's formula to express the value of the function to point z inside a circle C as an integral over the circle C. We then expand this term 1 over zeta minus z in powers of z over zeta, leaving a remainder term. And when we put that into the formula we got from Cauchy's formula, then we finish up with f of z is equal to a0 plus a1z plus a2z squared, and so on, plus a remainder term. The a's there, the coefficients, are complex numbers, but they're given in terms of integrals involving f around the contour C, the circle C. Then we have to show that the remainder tends to 0 as more and more terms are taken in the series. And that's a slightly complicated argument that involves the estimation theorem, you remember. But the important thing for our purposes is to remember that it works because z lies inside C, and so when zeta is on C, mod z over zeta is less than 1. And finally, we tidy up, and by that I simply mean that we recognize that the coefficients a sub n are given by the usual things for Taylor's series. Now, how much of that can we adapt to the case of this theorem about Laurent's series? Well, the first thing, of course, is that f is analytic not on the disk, but on the punctured disk. The next step is to use Cauchy's formula, but of course that's going to be a bit difficult with f having a singularity at 0. And so we've got to think of a way of getting around that. Well, here's the punctured disk on which f is analytic. Here's a point z. We take a circle C2 lying outside z, another circle C1 lying inside z, and we can construct a contour as follows. Join those two circles along a straight line, and we'll go once round C2 in the positive direction, in along this line segment, then around C1 in the negative direction, then back along the line segment. The point of that maneuver is this. So I've constructed a contour like this, which encloses Z, and on which the function is analytic. It lies in a region in which the function is analytic. It so happens that Cauchy's formula will extend to cover that situation. In other words, we can express the value of the function at z in terms of an integral around that contour. What does that give us? I'll write it on the board over here in the next space. F of z is equal to 1 over 2 pi I. It's the integral of f of zeta over zeta minus z, d zeta, but around this complicated contour. And what have we got on the complicated contour? Well, we've gone once round C2 in the positive direction. We're going to go once round C1 in the negative direction. I run out of space a bit there. Let's make a bit more space. Once round C1 in the negative direction, so that's where the minus sign comes from. Once out along that line, once back again, and so those two things cancel out. And here's our generalization of Cauchy's formula. What was the next thing that we had to do? The next thing that we had to do was expand something or other in powers of z over zeta. Well now, remember why we expanded in powers of z over zeta? It was because we wanted z over zeta modulus to be less than 1 to make the remainder work. This time, we've got two circles to think about. The point z, remember, lies inside C2 and outside C1. So for the circle C2, I've got to get this right, it's a bit complicated. The circle C2, then z over zeta, if zeta lies on C2 and z is inside C2, mod z over zeta would be less than 1, so we can expand in terms of z over zeta for C2. For C1, z lies outside C1, so z over zeta will be greater than 1 in modulus. Zeta over z will be less than 1 in modulus, so we'll expand in terms of zeta over z this time. Okay? And when we do that, we'll get, put it in the two integrals, we'll get a term which, a series which is very much like the thing that we had for Taylor's series from the first integral, plus a remainder term. Let's call that remainder 2, because it goes with C2. But when we put this in here, we're going to get things involving 1 over z and 1 over z squared and so on. And that's the sort of the complicated part of the Laurent series coming in. So let's write that as a sub minus 1 times 1 over z, plus a sub minus 2 times 1 over z squared, and so on, plus another remainder 1, because it's to do with C1. Okay? So there we are. The coefficients a in there are complex numbers, but they're given in terms of integrals involving f around these circles. Now then, the next step in the argument, if you remember, involved the remainders. We had to show that they tended to 0. The remainder in Taylor's series tends to 0 because mod z over zeta is less than 1. The remainder here, this one, remainder 2, is going to tend to 0 because mod z over zeta is less than 1 when zeta lies on C2, so that will cope with remainder 2. The case of remainder 1 works because it's mod zeta over z that's less than 1. So there we are. The remainders tend to 0, and that establishes essentially the existence of the Laurent series. Final thing was to tidy up, and that meant to identify the coefficients. And really we're just interested in the one coefficient, the coefficient of 1 over z, and it's quite easy to calculate that. 2 pi I a sub minus 1 turns out to be the integral around c f of zeta d zeta. The calculation is quite easy. One point I'd like to mention, really it looks as though it ought to be a C1 here, but if you remember what's called the deformation lemma from Unit 5, that tells you that this integral is in fact doesn't depend on which particular circle you choose. So there we are. That's an outline of the proof of Laurent's theorem. And I think one final thing that I ought to do is to give you an example of the use of Laurent's theorem. Let's go back to the example as I had before. This is a function, remember, that has a singularity at the origin. And if I'm to evaluate that integral by using Laurent's theorem, what have I got to do? I've got to find the Laurent series for this thing and pick out the coefficient of 1 over z. Well now, 1 over e to the z minus 1, well, that's, if I take the power series, the Taylor series for e to the z, the 1 takes off the first term, and that leaves me with z plus z squared over 2 factorial, and so on, all to the power minus 1. I can take out a factor z. Remember, it's raised to the power minus 1, so it's 1 over z times 1 plus z over 2 factorial, and so on, all to the power minus 1. I can expand this power series, raised to the power minus 1, would be 1 minus z over 2 factorial plus and so on, plus z over 2 factorial, and so on squared, and so on and so on and so on. But it's only the coefficient of 1 over z that I'm interested in. I get a 1 over z from there, but all the other terms are going to, in here, are going to involve z or higher powers, so that's the only term involving 1 over z that I get. The coefficient is 1. The value of the integral is 2 pi I times 1. This is equal to 2 pi I. Well, there we are. That's an example of the way in which we can use this stuff about Laurent series to calculate integrals. And later on in the course, we're going to develop these ideas so that we can deal with functions which have several singularities, not just one, and so that we can deal with contours which are a bit more complicated than just the unit circle.